Thanks for joining.
Yeah, I wasn't sure if this is happening at 6 because Joseph said you will send another email on the mailing list.
Yes. So we postponed for 2 hours. Can you hear me?
Yeah, I can hear you.
Yeah, okay. Okay. It's my honor to invite Nashi to give us a talk. So Nashi is a postdoctoral fellow in the Department of Computing and Mathematical Science at the California Institute of Technology. She received her PhD from SMU in August 2023, and she completed her bachelor in electronic engineering at Tsinghua University. And her research interests include reinforcement learning, non-convex optimization, high-dimensional statistical estimation, and robotics, ranging from theory to applications. So thanks, Nash, to give us the talk. So Nash, you can start your talk.
Yeah, sure. How's the voice level? Will it be good or should I?
Yeah, we can hear you well.
Okay, good. Yeah, thank you so much for all the hosts. Yeah, and thanks, Xiaoding, for the nice introduction. Currently, I just joined Caltech for like 2 months. Yeah, CMS is actually kind of the computer science department in Caltech. Yeah, they will call it computing mathematical science. Yeah, today, welcome to this talk. I'm very excited to share some of our recent work to all of you, and hope this will be related to the topic of this seminar, like it's more about robust or safety. So the title is kind of, we want to see if we want to consider distributionally robust in reinforcement learning. What is the data price that we have to pay? Like how many samples do we need to learn a good policy? So this is a mean like the problem or the question like we want to answer in this talk. Okay, so thanks all my wonderful collaborators and Genli from the CUHK and Yuting Wei, Yuxin, and Yuxin Chen from UPenn, and material guests from Google Brain, and Wen Haoding from CMU, and my PhD advisor, Yue Jie. Okay, so I guess everybody, in this room gonna be familiar with RL, right? So I would just give some of the like background. So reinforcement is pretty successful recently and in a lot of tasks. For example, like ChatGPT or other things. So it was used to training the large language model or do the alignment. However, reinforcement learning can be pretty data starved. For example, to training the AlphaGo game, we're gonna need a data set of 30 million of moves. And if we want to train the StarCraft, we need like 200 years of data, like a lot of video to train it. So data efficiency becomes a very pressing need for reinforcement learning because of the task is very difficult and the agent need to explore the environment, which is unknown and maybe very large. And in another side is data collection may be very costly or time consuming. For example, for ChatGPT, like the big company need to hire a lot of workers to do the human feedback part, right? So it costs a lot of money and also will be time consuming. So we pretty want to learning an RL agent using as few samples as possible. So that's a big challenge for reinforcement learning and maybe all other artificial intelligence. And there's another principle which is very important, which is called robustness. I guess it is kind of difficult from the safety, like because safety people were saying we want some constraints and we will have some cost function, like we do not want to it get very large, right? But robustness is people usually want to consider some uncertainty. For example, the environment have some uncertainty, or the state have some noise, or action have some noise. So this is a ubiquitously phenomenon that will happen in our reinforcement learning tasks because of some simulation to reality gaps, or we want to generalize to some very kind of slightly different tasks. So the second principle that we want to highlight is the robustness in reinforcement learning against uncertainty. So this talk, the goal is we want to design such good, robust RL policy using as a few samples as possible. So this is gonna be the outline of talk. So very briefly, give the background of Markov decision process, which is the playground of RL people, and what is the real formulation of the one kind of the robustness in RL. So we can consider different kinds of robustness in RL, but so this talk we will focus on one popular, but it's a very specific type called distributionally robust RL. So what is a problem formulation? And then we're gonna try to answer, okay, how many samples do we need to solve this distributionally robust RL? Do we need more samples than solving standard RL or less? Okay, the second part is like if we come to offline setting and we also want robustness, so how can we design sample efficient algorithms? And hopefully I can cover all of them, but maybe we can focus on the first part. Then we can just see what's the time, and yeah. But feel free to interrupt me if you have any questions or any curious things about this work at any time. Okay, so far so good. Let's just briefly introduce what is the Markov decision process, which is the problem that reinforcement learning gonna be formulated as mathematically. So I will introduce some notations. It's just to keep us on the same page, that because such term gonna be important in the later if I want to show some results. So in a Markov decision process, we will denote as an A as the state and action space. And when the agent can receive some immediate reward when they get some state and action. So we denote it as R. And the policy that the agents execute, we denote as pi. And there's also one important thing called transition probabilities, which means, yeah, we will denote as P, which represent the dynamics of the environment. So then we can have the value function and Q function. Here, I just want to introduce these notations because for a fixed, so here the value and Q function, oh, sorry, there's a typo. So was represented for a fixed transition kernel, which means for a fixed environment P, what is the value function if we apply the policy pi. So here it's just add something in the superscript. Here the gamma gonna be the discounted factor. So we will consider specific discounted infinite horizon MDP. So which will lead to 1/1 minus gamma as effective horizon. And here the expectation was taken with respect to applying the policy pi for a fixed transition kernel P. So we know that the standard RLs want to maximize such kind of value function V pi P for a fixed policy P. Okay, then we have the background. Now we can introduce what is a distributionally robust RL that we want to learn. So motivation is the kind of the safety and robustness in RL, but this safety may not be the same concept as the safe RL literature. Yeah, just to note that. So the motivation can be, maybe we can just briefly say, if there's some sim to real gap, when the training environment and test environment is different. So we still want our policy not to overfit to the training environment. We want it to have some robustness that can still do kind of okay in test environment. So that's a goal. That why do we want robust in RL? So it comes to the question like, can we learn optimal policies that robust to such kind of model or called environment perturbations? So for example, this is just a brief task to show a thing that maybe we want a robust RL to do. So in the training environment, so the task is we want the robot to open the door. So in the training environment, we just put the door handle to be very high. Then, but in test environment, we put the door handle to be low, which is kind of the change in the environment. So there's kind of a model perturbation. Then the non-robust RL gonna fail because of our policy was too overfitted to the training one, right? So if there's some different thing happens, we're gonna fail. So that's the thing we want to solve. So whether we can consider a robust RL policy that can do well in both scenarios when the door handle is high or low. So that's the one example. Why do we want robust RL? Okay. Then how to model such kind of environment uncertainty mathematically or like in a more official way? We're gonna consider the uncertainty around the transition kernel because transition kernel represents the model dynamics, right? So that's why in reinforcement learning, when people consider distributional robust, they usually will consider the uncertainty around the transition kernel. But this can easily adapt it to the scenario that the reward also maybe have some uncertainty. So the idea is like we can suppose like the training environment is the transition kernel PO, which we say is nominal transition kernel. But the test environment P, which represent the transition kernel of the testing environment P, may shift from the training environment, so it's different. But but it won't be so far. So we still suppose that this testing environment will fall into a neighborhood around the transition kernel PO. So that neighborhood we will call it as an uncertainty set, which is an uncertainty that we want to consider. So it will denote it as U sigma PO. The size of the uncertainty set will determine by the radius sigma, and the distance metric for this like uncertainty set, or we call the ball. It can be chosen. It has a lot of choice, right? So if we want to consider the distance between two distribution points like P and PO, we have a lot of way to measure that. So people usually use, for example, F divergence, which is like total variation, such as total variation chi-square or KL divergence, or people use Wasserstein distance, or maybe other like LP norm. So with that, we can construct this uncertainty set. Okay, then we have some uncertainty set that we want to robust to. Then with that one, we can define the robust variant of value or Q function. Here we denote it as V pi sigma and Q pi sigma. So it's basically very similar to the like standard value function. The only difference is like we will put an infimum operator because we want to consider the worst case performance when the transition kernel P can be arbitrary thing in the uncertainty set that we just defined. So that's the robust value function and Q function. So distributionally robust MDP, or we call distributionally robust RL, what we want to solve is to find the optimal robust policy pi star that can maximize such kind of robust value function, which means we want a policy that can do the best in the worst case manner when the transition kernel can shift it around the training environment, but still inside the uncertainty set. So, and luckily, if we put some assumption on the uncertainty set, the one that we use here is called SA rectangularity, which is widely used when people consider such kind of distributional robust RL. We can also have the existence of at least optimal robust policy pi star, and we can denote the optimal robust value or Q function as V star sigma and Q star sigma. So which is corresponding robust value or Q function to that optimal robust policy pi star. Okay, now so far so good. It's like we already say what is distribution robust MDP, which actually just very similar to a standard MDP, except we define some uncertainty sets. And for such kind of robust MDP, we will still have a very good thing is we will have a robust variant of Bellman equation, which can ensure that the optimal robust Q function is a fixed point of such Bellman operator, which is very good because we can enjoy very good properties that's very similar to standard RL. And according to that, we can design distributionally robust value iteration, which means if we apply this rule again and again, iteratively, we will finally goes to our optimal Q function. So that's will inspire a lot of algorithm design that can happen very good. Okay, so that we already introduced like some basic and the problem formulation and some very preliminary fact of distributional robust MDP. Now we can come to our topic, like if we want to solve such kind of distributionally robust RL, how many samples do we need? Especially if compared to standard RL, it will be harder or easier in the sense of the sample requirements. So this is a very curious and open question. Except some prior arts, we are very curious about this, and it's also a very open question for now. So to understand this, we need to like model what is a sample we can get, right? So there's a lot of sampling mechanism in RL, and in theory, people usually consider, for example, generative model, which is this one, is the most fundamental setting. Like how can we get the data and use this data to train a policy? So basically, we will assume we have a simulator that for any arbitrary state action pair, we can randomly and independently sample from it. Sample from the nominal transition kernel. That's conditional on such state action. And we can get the randomly sample next state S prime. That is sample from this distribution PO. Then we can have a lot of such kind of tuple, like SA, S prime, and also the reward. So we call this one sample, then we can do a lot of we can collect a lot of samples, and we can have a data set D, which consists of n samples, but it's only from the nominal environment PO. Then our goal of solving distribution robust RL is we want to find a good policy, right? So we will say for some accuracy level epsilon, we want to find an epsilon optimal policy, which means the performance gap between applying this policy pi hat and the optimal policy gonna be bounded by epsilon. And we want to achieve this. We want to find such policy pi hat using as few samples as possible. So we want to see what is the minimum of n that we can achieve such kind of goal. And then we focus on understanding some widely used and popular algorithm, which is one kind of the value-based policy called model-based RL. So for model-based RL algorithms, there's like 2 steps. The first step is we use the datasets D to estimate an empirical nominal transition kernel, PO hat. Then after we get this one, we just use some planning oracle to do, like, for example, policy iteration or value iteration. Then we can find the optimal policy according to this empirical nominal PO hat. So that's basically what model-based RL will do. So it's like 2 splitted steps. So there's a very promising model-based algorithms, which introduced by, like, in 2025 by 2 concurrent work. So which means we just use a very very simple, like, distributional robust value iteration as the planning oracle, and based on the empirical transition kernel PO hat, and we can arrive at a very good solution. So that's the algorithm that we want to understand. Now we can have now there's a very interesting question. It's like, after we use the data set to get an empirical nominal transition kernel PO hat. So for standard RL, their goal is we want to learn the optimal policy just for this fixed and the same nominal transition kernel MDP. But like robust RL, what we want to do is, like, we want to learn the robust policy that can do the best in the worst case around the nominal MDP, so that the transition kernel is not fixed anymore, which may need, so it's very curious, like, which one will need more sample. Because we can see, like, if we say this distribution robust value iteration carefully, you can see actually it's very close to a standard value iteration people use for standard RL, except for this part, this infimum operator, which will lead to a additional inner problem, like additional inner optimization problem when we want to do such kind of robust value iteration. So it would be very curious, like, because we have such kind of additional inner problem, whether do we need more samples or less samples than standard RL. So we want to understand from a statistical perspective, do we need to pay more samples price if we want to solve a robust RL compared to a standard RL? So that's the question. And it's very open, is because regardless of the divergence function that people use to construct such kind of uncertainty sets, all the existing work cannot have a very affirmative answer for this question. It's because, for example, if we use the total variation distance as to construct our uncertainty set, then the purple line is existing like state-of-art upper bound for the distribution robust or for some algorithms. So which means the left-hand side data like the order is so we require such kind of maybe I can do the sorry, I'm trying to do annotation. Okay, just skip that. Yeah, I'm just not sure whether you can see my mouse, but yeah, the purple line, which means if we want to achieve a good policy, a good robust policy, or if we want to solve distribution robust RL, the purple line gonna be the sample that we need so that's the best we can get for some algorithms. And the green line represents the lower bound, which means if we want to solve a distribution robust RL, the green line gonna be the sample, gonna be the minimum sample that any algorithm needs if they want to solve it. However, like the blue line is the sample requirement to solve a standard RL. So we can see like because of the purple line is very far from the green line, which means there's a very large gap between the existing upper and lower bounds. There's not a good answer. What is the real sample requirement to solve a robust RL and to solve such kind of robust RL? And especially one is higher than the standard RL, and the lower bound is lower than the standard RL's line. So we are also not sure whether solving robust RL is harder or easier than standard RL. And in another example, like if we say like chi-square uncertainty, which means if we use chi-square divergence as a measured in the uncertainty set, it's still the same, like even worse, because like the purple line is very far from the green line, which like large gap between the upper and lower bound, and also not sure because of their comparison to the standard RL's requirements. So for this, to answer this question, we developed the statistical understanding for both TV uncertainty set and chi-squared uncertainty set. So in TV case, what we do is like we provide both like new upper bound and new lower bound, and they match with each other, which means we establish the minimax optimality of solving such kind of distributional robust RL under the TV case. So if we illustrate the results, we can see the red line is the result of this work. So the interesting is like because we got our upper and lower bound matched, which means the red line is exactly the sample requirement to solve a robust RL policy if we use the TV uncertainty ball. So this is interesting because we not only like, okay, improve the upper and lower bound, but we can have some new message. We can say like, actually, solving a robust RL is easier than a standard RL, right? Because the red line is lower than the blue line, which means we're gonna need less sample to have a good robust RL policy, especially when the uncertainty level sigma goes to kind of big. We know like 1 minus gamma is actually very small. So this is a very interesting message because although we have an additional inner problem to solve, we're gonna need less sample. Then if we come to chi-square uncertainty, we also develop like both the upper bound and lower bound. And if we see the results, the information comes actually from our lower bound. So the upper bound is actually just tightened, but the interesting happens is we can see the red line is higher than the blue line, which means, so the red line represents the minimum size of sample that we're gonna need if we want to solve a robust RL using the chi-square uncertainty ball. So in a lot of range, when the sigma like bigger than 1 over 1 minus gamma and keep grows to infinity, or when sigma is kind of a constant level or just a little bit bigger than 1 minus gamma here, we can see like solving a robust RL will be much harder than standard RL actually, in the sense of the sample that we're gonna need. So this is a two very different message comes. So the takeaway message from statistical side is like solving robust RL is neither harder or easier than standard RL. If in terms of samples that we're gonna need, it will heavily depends on the shape and size of the uncertainty set that we prescribed, defined. So different uncertainty set gonna lead to different difficulty. So this motivates us, or in practice, we want to design our uncertainty set very carefully. And another message is like, from if we say the TV case, we can see like actually distributed robust, such kind of robust formulation for RL is potentially more sample efficient. So there's some advantage of robust formulation. To say that, I also want to, so we can come back to this case. So this is, we already show like the distributional robust formulation in RL may have some theoretically statistical advantage, just in some case. So what about the practice? There's one interesting happens. So let's recall what is the task that we want to solve is we want our robust RL agent can do well no matter the door handles high or the door handles low, right? So we want the robot can put the door open. So after training in one of our empirical work, so what happens is very interesting. Like if we train our robot using a robust RL formulation, this is the result we get. So the robot no longer want to handle with want to deal with the handle. It will find some cheating actions, right? So it's very interesting because it's it may be a more general way. Like, yeah, so it's not only a robust RL formulation can find can deal with some maybe uncertainty. It may lead to some more general way to solve the problem. So that's just inspiration, yeah, for practice. And yeah, this is our new work on also happens in these NURBS. Yeah, feel free to check our website if you are interested. Okay, let's go back. I think that's pretty much the first part that we want to see. The takeaway message is like maybe robust formulation for RL have some advantages from statistical perspective and also from some practice perspective. Okay. Then let's come to a little bit technical detail, like about the intuition. So why solving robust RL is easier or harder than standard RL? Oh, sorry. Okay. So let's see what is the difference if we want to say if we want to control the error of standard RL or robust RL? So recall that we already have an estimate of the nominal transition kernel PO hat, but this one gonna not be the real transition kernel PO. We do not have any knowledge of the PO, right? So for standard RL, what people want to control is actually this term, delta RL, which means it's the distance between the Bellman operator and the empirical Bellman operator for some value function V hat. And it's gonna be linear with respect to the model estimate error, PO minus PO hat. However, when we come to robust RL, things gonna be more complicated because the robust Bellman operator and the empirical Bellman operator gonna have some additional inner problem, which leads to a complex and also maybe nonlinear form, which is gonna be very nonlinear with respect to the model estimation. So this is the actual challenge that we need to consider when we want to deal with robust RL. So there are gonna be two facts that influence this error. So the first one is the form of this function. So what is the relationship between the error and the model estimate error PO minus PO hat? And another one is the range of the value function, because like we know, like robust RL and standard RL actually is to solve it's actually two different problems, and the value function or the max or the final thing we want to maximize is different. So the V hat is the thing that we want to estimate in standard RL, but the range of it may differ from the robust RL, robust value function, which actually is a key if we want to achieve a slightly better like sample complexity when we in TV case. So for example, for TV, because of for the first factor, we will the error term will have linear dependency with respect to the PO minus PO hat, which is very similar to the standard RL. So this part won't change compared to standard RL. So why in TV, why we use TV, but we may need less samples, because the range of the robust value function will contract rapidly as our uncertainty level grows. Then it will be smaller than the range of the value function standard RL. So that's why the final error will be smaller than the standard RL. So that's the key why we have less sample requirements. Okay, so that's a small range of this one. So for chi-square, why we need a lot more sample than standard RL is because the first factor actually, the nonlinear and sensitivity of the function, error function with respect to the model estimate error. So which means even if our model estimate is very accurate, the error term of the robust error can still explode because of the uncertainty size shape. It's kind of weird than the TV case. Yeah. That's the main intuition why we have two very different behavior of the sample requirements when we consider different uncertainty sets from the theoretical intuition. Yeah. Okay. So I may just briefly introduce the second part, or okay. So in about 10 minutes. So basically it's like last part we mainly focus on understanding the statistical, like what is the sample we require minimally, like we need if we want to solve robust RL. Then how can we design algorithm to achieve a more sample efficient algorithm? So we considering an offline case, which means we only have some history data set, and we do not have the access to further interact with the environment. So how can we design a good, robust RL policy based on only some history data set? So if we see the sampling mechanism difference before compared to the previous generative model case, it's like we no longer can get any sample from the state get sample from any distribution around the state action pair. It will be determined by our history data sets. So we can assume we have data set that has some distribution on state action called DB, and which is sample from some nominal transition kernel still. So have such kind of history data sets. The difference is like we cannot decide where do we want to sample, right? So the data set already be fixed when we got this history data set. So the history data set may be good or bad, we have no idea. But the goal is still we want to learn an epsilon optimal policy according to such kind of history data set. So here is so we consider another different uncertainty bowl using KL divergence. So here's the prior art, which means they design some algorithm that can achieve such kind of sample complexity, which means they need so many sample to arrive at a good policy. So the question is, can we further this is very so the sample complex, it is still very sample efficient. It's because we can see the algorithm gonna need at least I square, the sample size that's scale with I square. So state space as is the size of our state space, and it can be very large. For example, in Go game, the state space can be in the order of 10 to the power of 171. Or in StarCraft, like in video, the state space may be more larger. So the question is, can we design a better algorithm to improve the sample that we need? And also we want to achieve a good policy when even if the history data set is not good. So that's the two things we want to do. So okay, let's so to quantify the history dataset quality, people usually use some single policy concentrability coefficient. So here we develop a robust variance of it to quantify what is the quality of our dataset. So intuitively, this is the C-Rob star just describe the discrepancy between our history dataset and the optimal robust policy that we want to achieve. So it's like if our history dataset is more like a history dataset, it's more like a dataset that's we can get if we run our optimal policy, then this C-Rob star gonna be more small. So, and this C star, if it's finite, it allows the history dataset to be partially covered, which means it don't require the history dataset D to cover the entire state action space. It only needed to cover the space that the region that the optimal robust policy gonna cover. So that's the thing that we're gonna have this assumption for this history dataset. Then we can develop an algorithm using a very popular principle called pessimism in offline RL, which means the only difference, like compared to the previous distributional robust value iteration, we only add one penalty term, which is this B. It means it will quantify the uncertainty set, which is not the uncertainty set around the model anymore. These uncertainties come from our data. So if the data is good, then this penalty gonna be very small. If the data is bad, this uncertainty gonna be good, but gonna be very large. So actually in offline robust RL, we're gonna need to consider two different uncertainty. One is our model uncertainty, another is the data uncertainty. And we need to carefully design this pessimism term which is a tighter, which is a very tight upper bound for the following term. But this one may not have some closed form because we have some inner optimization problem we need to solve. Then we can decide what is this. So that's the main key part in the algorithm. Then we can show what is the sample size we're gonna need for this algorithm. And we also show a lower bound first. So we developed pretty much until now the only lower bound for this problem. So if we use offline RL and KL divergence to construct the uncertainty set, so the yellow line gonna be the best that an algorithm can achieve, which means the minimum sample that an algorithm requires to get to a good robust policy. So the P mean here is actually represent the minimum positive transition probability of a nominal transition kernel. So we can see the lower bound actually skew with this term. And we also show like the designed distributionally robust value iteration with the LCB, which is the penalty term, can achieve almost match or minimax lower bound here. So we can, it actually means our algorithm can achieve near optimal sample complexity. So that's the result for the offline case. Yeah, just briefly introduce it. If you are interested, please feel free to check the details. So, okay, we can skip the numerical, come to the conclusion part. Then we can maybe have some question if we want to ask. So the one take-home message is like solving robust RL may not be harder than robust RL, but also not easier. Like it heavily depends on the uncertainty set that you want to consider. And another one is like we can also try to use some pessimism technique to develop near optimal sample efficient algorithm for a robust RL if we consider offline case. Okay, that's all. And here's the reference. Yeah, welcome any questions. And that's, I think my talk just ended. Yeah.
So thank you for your great talk. So I have a question. So
Sure.
do you use sigma to measure the policy uncertainty, transition uncertainty?
So the sigma means the
in this first part.
Okay. Yeah, we can get back to that. So this is sigma. Sigma just means the radius of your uncertainty ball. Yes. So when sigma grows, your uncertainty set will grow. Yeah.
Okay. What if we don't know the sigma?
Yeah, good question. So for now, people will see we can, for example, we want to train a robust policy for some task. Then people will do is like they will define some prescribed uncertainty sets. So basically, it's a sigma that you can define yourself, and also for the rho, which is uncertainty like the divergence function, you can also define yourself. But the good question is you'll never know whether the sigma and the rho is a thing that you want for this application task. Yeah, I think it's one of the key in practice. if people want to use such kind of robust framework, they have to carefully see what is actually the robust uncertainty set they want to use for practice. Yeah, so that's why. So that's why I will say this one's interesting, is because So basically in this empirical work, like so we kind of try to learn an uncertainty set for tasks. So we do not do like define a prescribed one, like just by heuristic design. We can learn something, then we can see what is the uncertainty set that we want from some machine learning tools, like for example, neural network or causal graph, something like that. Yeah.
Okay, thanks.
Yeah, very good point. Yeah.
Any other question?
Hi, I also have a question. Thank you for your presentation. So I wanted to ask that,
Yeah, thank
was
you.
was there any specific reason that you chose these two distance? For example, is there any specific reason that you didn't try the Wasserstein distance?
Oh yeah, very good point. The basic things like because total variation and chi-square is used in some practical robust RL work, so that's why we first consider this. And Wasserstein distance is also considered in the practical work. And I think it's a very good direction to investigate more about more like divergence function, like Wasserstein distance, because it's widely used in supervised distribution robust optimization. Yeah, I think that's a very promising. Yeah, actually, it's very promising. And there's only a few theoretical work from I know there's only one existing one about what's the distance if we say from the theoretical part. Yeah.
Also, did you see any difference in practice between these, for example, this chi-squared or TV distance? But for example, in the opening the door example you mentioned,
yeah,
when you're trying, did you see any difference between these two distances?
Yeah, good question. I think for this practical work, we mainly do is like we learn a specific uncertainty set, and so it will not use any heuristic divergence. So we didn't do like the experiment for some explicit divergence function, for example, TV or chi-square. So it's pretty much a very learning-based uncertainty set. So, but that's a very good question. I haven't seen some comparison in practice, like whether we should use TV or chi-square, and what is the difference. I think that's a very good thing to demonstrate if we want to further understand the practical, which one is better or something like that.
Yeah, because for example, in the TV case, you mentioned that the sample complexity is even lower than the standard RL. So if that's the case, then TV would be much better than the chi-squared if there is no difference in the performance.
Yeah, that would be a very interesting thing to see. Yeah, I think that's a very good direction. Like I may need to add some experiment. For now, this is pretty much a more theoretical result, but I think that would be very helpful. Yeah, maybe in some like very simple grid example, then we can show whether TV will really have such kind of bonus, like much less sample gonna need. Yeah.
Yeah. Thank you so much.
Yeah, very good. Yeah, very good comments. Thank you so much.
Okay, hello, thank you for your talk. I have just another question about an outer look of robustness
Sure.
optimality. And maybe on slide 27, which we are seeing the two performances of the two distance metrics.
This one? Oh, yeah.
Yes. So here, I mean,
Okay.
one result is that when the amount of uncertainty, the sigma is increasing, by TV uncertainty, we have actually reaching lower sample complexity. And on the other hand, if we use it's going higher. So my actually outlook, as I'm not that deep into the details of robust reinforcement learning, but I want to connect it what I know from robust control, and also like achieve control, that usually robustness is against optimality when we are forming the min-max optimization problem. So if we consider that the uncertainty is in the observation noise of the robot that is sensing the environment, so as much as this observation noise is higher and we want to solve this robust MDP problem, then the robot is showing more slower motions to attack those uncertainties, for example. And so what I wanted to ask here is that if the problem of defining the uncertainty shape here actually also changes the optimality, or maybe the amount that this TV uncertainty and a chi-squared uncertainty are defining here have different optimal solutions in the end.
Yes, I totally agree with that. Yes, that's right. So if we use different uncertainty sets, the shape or the size is different, we may lead to different optimality solution. So that's why I consider robust formulation maybe is a good one to study further, because, for example, in this case, it's basically why they choose to have this cheating, but maybe better than I expected solutions, because the formulation is different, right? So the optimality is not just focused on one, like for example, the training environment. This case, the optimality in the training environment, if we use non-robust RL formulation, is just to open the door and when the handle is fixed here. But when we come to a robust RL formulation, maybe your optimality point already changed. So that's why they can come to this optimal solution. Yeah, I totally agree. Using different uncertainty sets is actually lead to different optimality solution, which may be good or may be bad for a specific task.
Yeah, and to continue on that, maybe I just, for example, in most of like reinforcement learning papers, that they are comparing several methods in mainly not on the standard RL, they are showing the performance on, of course, curve of the convergence of the rewards for the specific problem. And that's basically how they are showing that in amount of how many time steps or sample data, then they can reach the optimal reward. And to me is that, for example, if we don't know that when we are having a TV shape or a chi-square shape for uncertainty, the amount of the algorithm is reaching the same optimal solution, then we cannot really judge, for example, which one has lower complexity or high complexity in the end, because the complexity depends on what the agent is trying to train in the end and reach in the solution.
Yeah, totally agree. I think most of the people, for example, when RL, they will add, for example, some entropy regulation, right? Then they show, okay, the convergence rate maybe is faster if then we don't add some entropy in the reward. Then yeah, I agree. Like, it's actually because they are two different problems. Yeah, just so the optimality point will be different maybe. So yeah, it's not a fair actually. Yeah, I agree. It's not fair. It's just people want to see maybe for example, adding some entropy such formulation, we can get a quicker algorithms, but we may not actually arrive at the original optimality, which is the one that we don't add entropy. Yeah, that's also happened here. So that's why we can see, okay, we can see like, well, the robot, we can just see, maybe we can just see using different uncertainty sets, what is the sample complexity, but we cannot like really see if we achieve an algorithm here, then it's better than here, right? So because the performance metric is different. Yeah.
Thank you so much for a nice presentation.
Yeah, thank you so much for the question.
Do you have any questions? Okay. Thanks for your talk, Nancy. Okay. I think that's all.
Yeah, thank you for hosting and inviting me. Yeah, thank you. Thank you, Joseph. Thank you, Shandi. And thank everyone here. And if you have any questions, please just reach out to me. Or you can just search my website. Yeah, I didn't have a like, okay. But yeah, you can search my name and contact me for any question. We can talk offline. Yeah.
Okay, thanks.
Thank you very much for your talk also from my side. And Shangding, I think we can close it now. So thank you all for joining today. And keep up, register on our website for further news, further talks, SafeRL online seminar. So I'll just send shortly the link in the chat before we leave the meeting, and keep up with the mailing list for more news on the coming talks. Thank you all again for joining. Sorry for the confusion with the time, and yeah, we see us next time.
Okay, see you next seminar.
Thank you. Thank you.